Hello, everyone, and welcome to my talk on coupling of models for fire dynamics and pedestrian dynamics to estimate the required safe egress time. My name is Kristian Börger, and I'm a researcher from the Department of Computational Civil Engineering at the University of Wuppertal. And this is a joint work with Mohsin Shaibi from the modeling division of the Department of Pedestrian Dynamics at the Jülich Research Center, which is part of the Institute of Advanced Simulation. Today I want to talk to you about the importance of open source software in research and how an approach could look like to couple open source models for fire dynamics and pedestrian dynamics on an example of people walking in an environment with impaired visibility. So first, let me start with a short outline on the talk. So I want to start with introducing you into the importance of software in modern research, which brings me directly to the motivation of that talk. Then I want to give you I want to introduce you into 3 Python libraries that were developed at the University of Wuppertal and the Jülich Research Center, which are JupyterSim, a Python package for simulating pedestrian dynamics. Then we have the FDS reader, which is a fast and easy to use Python reader for FDS simulation data. And built up on that, we have the FDS VisMap Python package, which is a tool for waypoint-based assessment of visibility and performance-based fire safety design. And last but not least, I want to close with an application example on coupling multiple of those tools and finish my talk with a short outlook what is still to come on this field. So first on the importance of software in modern research. So while commercial software often provides robust features, it comes with limitations that make it less suited for scientific purposes. We have, for example, the high costs, the closed source nature in general, and restricted licensing. But in general, this software is quite easy to apply, easy to use. So which makes it an absolute necessity of this kind of software, for example, in daily engineering work. But it's not very suitable usually in research because we have limited connectivity to other software and not all of the required parameters are adjustable in general, for example. On the other hand, open source software offers several advantages which are crucial for researchers, which are, for example, the cost effectiveness. So the open source software is typically, so not generally, but typically free. We have transparency and reproducibility, so we can inspect, modify, and share the code. And developers of open source code usually encourage people to collaborate, which is accelerating the innovation and problem solving on the software. And we have the flexibility and customization. So adding new features or improving existing ones can be done by yourself without waiting for commercial updates. This brings me to my motivation for the work presented in this talk. When I talk about coupling models for pedestrian and fire dynamics. So there are models for this purpose, like the FDS and evac, for example, which is a great tool for pedestrian dynamics and coupling, fire dynamics and pedestrian dynamics. We can directly consider the results from the FDS simulation in the pedestrian dynamics and the impact of that on the movements of agents and so on. But the thing is, the FDS evac is not longer supported, so it has been discontinued since FDS version 6.7.8, so which makes it kind of obsolete and not relevant anymore for research purposes when there's no support anymore. So our goal was to connect existing libraries for pedestrian and fire dynamics that are still constantly developed and improved. Which brings me to the first tool I want to introduce to you, which is JupetSim. This is a Python library for pedestrian dynamic simulations with a native core for performance-relevant tasks. It was developed at the modeling division of pedestrian dynamics at the Jülich Research Center. And the benefit of this one is so that we have an open source tool. We have an open source Python API where we can change the state of the simulation at every iteration, every time step, allowing to implement strategical and tactical, or to allowing to implement on a strategic and tactical level several things like route decision, walking speed, or behavior of the agents, which allows a quick, which allows experimentation, for example, on a very quick level. And the software can be assessed by basic elements, basic scripting elements that are provided for wayfinding or scripting queues, axis, and also for modeling of the whole geometry of the cases. JupetSim itself is written in C++, so the core is written in C++, which bothers the basic behavior like routing and movement, for example, here based on the social force model. And this core should usually not be touched in most application cases, and also in general not in any research cases. For that reason, on top, we have a Python API to control most features of the software, as I already said, like building geometry, defining the routes, and setting or updating route decisions at every step of the iteration. And in between, we have a C API as a connection of both levels. So next thing I want to introduce you to is the FDS reader, which is a Python library that was developed also at the Jülich Research Center, but at the Fire Dynamics division, and also at the University of Wuppertal. And this one is a library it is a Python library to read most of the FDS generated output data, and to map it to Python-like data structures, for example, NumPy arrays. So we can read the data from point devices or two-dimensional and three-dimensional slice files, or also boundary files, for example, and map them to multi-dimensional NumPy arrays. And also we can read metadata from the simulation, like the time steps and so on, and also the obstructions geometry, for example. So before introducing the next library here at this point, the FDS VisMap Python package, I want to lose some words about the assessment of visibility and performance-based design in general. So performance-based design for visibility in case of fire usually still relies on Gin's law, which was developed or empirically derived from experiments with people looking through a glass window on exit signs, and then seeing on what smoke density, on what extinction coefficient from the smoke an exit sign or a visual target can still be perceived or seen by the participants of the study. And Jin derived an empirical correlation here, defining the visibility at the visual range at which the target can still be seen. And the correlation is between an dimensionless empirical factor for the sign, saying if it's a self-illuminated sign or a light reflecting sign, and the light extinction coefficient of the smoke. And in performance-based design, this data, this extinction coefficient data, can usually be obtained from the simulation results. Like in FDS, you can have a two-dimensional slice file offering spatial and temporally resolved data on the extinction coefficient, on the local extinction coefficient of the smoke, which lets us derive a kind of a local visibility at each point in time and space. So the problem is with this approach that it neglects an inhomogeneous distribution of smoke. So when we're just looking at a single location and we compute a single value for visibility that does not say much about the relative visibility to an actual exit sign, and that is at a certain distance I'm looking at. We also neglect that there might be a reduction of visibility by the view angle on what I'm looking at the sign. So the perceived area of the sign reduces at larger angles, larger view angles. And also, we do not consider visual obstructions in the line of sight between the agent or the observer and the exit sign if you just look at a local visibility. And last thing is, usually there is, when we assess visibility in performance-based design, a general or an absolute performance criteria that is set for the whole domain, and this one is usually chosen based on if the people are familiar with the facility or not. Then we have a visibility of 10 to 20 meters, which is usually used in literature. Yeah, as I said, depending on if people are familiar with the building or not. So it has nothing to do with an actual required visibility to see or perceive an actual exit sign. So the idea to overcome those drawbacks was to create visibility maps as floor plans, indicating locally and temporally whether the performance criterion of sufficient visibility is met or not. So the idea is that visibility should not be calculated as a local quantity, but relative between the person or an agent and an exit sign. So we compute an integrated or averaged extinction coefficient between each cell of the domain and the exit sign, or the waypoint here. And second is we want to consider if there are any visual obstructions between the agent and the exit sign, and we want to have a reduction of visibility based on the view angle on the sign. So this is the idea behind this. And all this should be done without without much further effort, but just post-processing existing data from fire models like FDS or any other CFD codes. So how should that work? So for example, here we apply a ray casting algorithm. So we cast rays from our waypoint. So our waypoint is the exit sign that is that an observer looks at. So the observer can stand or can be at any cell inside the computational domain. And then we cast a ray at all of these cells inside the domain and see if the waypoint is concealed by any obstructions or not. Oh, sorry. And second is we, by casting a ray, we can select cells in the line of sight between the waypoint and an observer at any cell, and we can select cells to compute an averaged extinction coefficient. And from the average extinction coefficient, we can then calculate for every cell and every point in time here a relative visibility. And the visibility maps in the end are then aggregated from several matrices or arrays, 2D arrays, by logical and mathematical operations. So we set up several matrices. So as I already said, we have a matrix indicating whether specific cells are concealed or not concealed by obstructions. Then we have a matrix that has values for the reduction by the view angle, depending on from where I am looking at the waypoint or the exit sign. Then we have a matrix with the integrated or averaged visibility values. And from that, we can aggregate a visibility matrix or a visibility map. The aggregated visibility matrix. And so at this point, we do not have to compare the visibility values to randomly chosen performance criterion, but the performance criterion can directly be derived from the distance of each cell relative to the waypoint. So it's quite easy. We just match the aggregated visibility map to a distance matrix, and then we get a visibility map indicating for each cell if the waypoint or the exit sign is visible or not. So this is the basic idea behind the visibility maps. I want to demonstrate on a simple example of an office building how coupling of fire and pedestrian models could work using all the libraries and tools I introduced to you. So here we have a simple example of a small office building where a fire occurs in a small room here and spreading smoke over this foyer, and later on in this corridor. We have two spawning areas here where agents are consistently and randomly distributed generated, and we have two evacuation routes. So we have evacuation route 1, which is the preferred one. So all agents would go for the evacuation route 1. And if evacuation route 1 is not accessible anymore, the agents may switch to the evacuation route 2. And last, we have the exit signs over here being waypoints for the FDS VisMap package. So the pedestrian dynamics is performed with the JupyterSim software, while the fire simulation is performed with FDS, and the visibility data is post-processed by the FDS VisMap package. And at every time step, at every iteration, the visibility data is read from the results of the FDS VisMap package, and then the walking speed of the agents is adapted, and the route decision as well. So first, based on the visibility maps, which I just showed you, which are those Boolean type maps, the red and green colors, they are aggregated over several time steps so that we can get these ASAT maps indicating the first point in time at which a specific exit sign is not visible anymore. And we do this separately for the evacuation route 1 and evacuation route 2. And we see that for evacuation route 1, that just in the foyer, we have an impact of impaired visibility, while the corridor and the spawning areas of the offices are not affected here. And the route 2 is not affected in general. Here on the left side, we see the smoke distribution in the FDS simulation. You see smoke spreading in the foyer and later on and in the corridor. And when we have a look on the pedestrian dynamics over here on the coupled model, it's not yet working very well, but it's just first try for coupling those models. It's more about the idea over here. You see that at first all of the agents are going for the evacuation route 1, and then later on, when the smoke concentration exceeds a certain level, the agents do not, or step into the room, into the foyer, do not see the exit sign anymore, and then switch routes to evacuation route 1. To evacuation route 2. Yeah, so that's it from my side. There was just a very short example, not very complex yet, but just to give you an idea on how the coupling should work. So what is still on our list is to have a more intelligent route decisions of agents based on knowledge about the building geometry. We want to introduce communication of agents to avoid blocking of routes. So when the agents are walking through a door, some of the agents do not see the sign anymore, come back and block exits and stuff. So that's something we're working on. And then we want to include not only the effects of impaired visibility, but also from like toxic gases. So for example, here we want to go for the FED criteria to be considered as an ASAT criteria as well. And maybe at some point in time, doesn't have so much of a relevance right now. We want to have a two-way coupling, meaning we want to may allow the agent's actions to affect the smoke distribution. So this is a quite complex thing since we need to go back into the fire simulation. But yeah, this is something that is maybe on the wish list. Yeah, that's it from my side. Thank you. And now I'm open for your questions.
That's not what I see on my screen. Hey, good morning. Thank you for joining.
Hello.
Yeah, thank you for the presentation. We'll just do a quick check here in the audience for questions. See if we have any online this morning. quite a nice talk. I think it'll be interesting to see if there are ways, to potentially share knowledge about, some of the new research that's being done and how that's being implemented in the various tools. It's nice to see that work happening. We do have a question here.
Yeah. Thanks for the talk, Kristian. One of the thoughts that came to mind, looking at the tools that you've done there, we've done a little bit of work post-processing FDS results to look at like early detection of fire or smoke with like cameras, and so doing a similar type of raycast analysis where you have the sensor location and the obstructions. So I didn't know if that was an application that you guys were looking at as well.
So I wouldn't say in that work, but in our previous work, we also did experimental work, so not on smoke detection, but on measuring spatially and temporally resolved extinction coefficients. We built or we developed a photometric measurement approach for that with consumer cameras that you put in an experimental hall, and then have a layer model where we can backwards calculate extinction coefficients. So maybe that's something similar to what you were talking about, but it's not like directly related to this work. So this is more on the application side and performance-based design.
Mm-hmm. And where that comes about is sometimes people want to have like cameras that they're using for the detector to get your time to detection for your RSET type calculations. And there's not really great guidance on how to use that in the CFD model, which is where we've kind of looked at that in the PBD space.
Sorry, can you repeat that? I'm not sure if I got the question.
Yeah, it might be a little bit quiet. Maybe talk more.
Sorry. In the PBD space, this has come up for us a few times where people want to use cameras to get their time to detection for the RSET. And so they want to know, well, where do we need to put our cameras? What types of cameras, or what size fire do we need before the cameras would be able to see them? So it's pretty applicable to PBD and where people are wanting to go now.
Yeah, that's right. I think so too. So so I'm not too much familiar with that stuff on the pedestrian side, because I did this work together with my colleague Marcin Schreiber. He's from the pedestrian division. But yeah, it sounds that it's quite an application case for this techniques. Yeah.
Thank you. Any other questions in the room? Here.
Hi, Kristian. This is Randy McDermott. Nice to see you. Thanks for the very nice talk.
Hi, Randy.
So it seems it's nice. There's an open source sort of tool to replace evac. I wasn't sure if I understood the workflow that well. So like when you run JUPED Sim, does that interact? I mean, can you visualize the agents with your own tools, or do you have to? Is there a way to get them as like particles in smoke view or something, like the way you used to be able to look at things in evac, or what's the vision of how tightly coupled this will be with FDS and so on?
So first, maybe to the coupling. So the coupling is just done by we have the visibility maps as I showed the ASET maps as three-dimensional arrays, so 2D layers at every time step, and we can read from that data and kind of transfer at every iteration step to the JUPED simulation, and so we can access every iteration step. And then to come back to your other question, so visualizing the data from JUPED Sim can be done in several ways. So unfortunately, there was a video in my presentation, but unfortunately did not work. So the smoke view and JUPED Sim should should have been videos, but unfortunately did not run. So the JUPAT sim data can be visualized either in a separate tool that was also written by the colleagues at the Forschungszentrum in Jülich, but it can also be displayed by, I think it is just plain matplotlib Python library. So you can just read the data in Python and look at it as a video or several pictures.
Okay, very cool. Thank you.
You're welcome.
Yeah, I think there's still the benefit of the FDS evac is always that it ran at runtime with FDS and had access to sort of the runtime data available in the FDS data set or in data arrays, and could react to that as the fire evolved. Most tools that are available are all post-processor type, where even if it's running alongside, it's still waiting for data to come out of FDS, but in some output form. It's not reading the, it's not in the operational space being able to read the data directly. So it's kind of a limitation that I think all tools share right now until they're in the FDS simulation code running as part of the FDS simulation itself and accessing that whole data set. It's always sort of a post-processing function of the data that gets kicked out. And so you have to have some nice outputs, like we were talking about 3D slices or Plot3D or 3DS, SM3D or whatever, some way to access that data closer to like runtime, but still it would be not the same as what data FDS has access to. So,
yeah, that's absolutely right. There's also kind of a drawback of our tool right now. I'm not sure how big the loss of that actually is when I consider in advance simulating different cases that might be not worst case, but worst credible cases. But yeah, anyway, so it's still a downside of not having the direct coupling. That's true, yes.
Yeah. Anything else? No? Okay. All right, thank you for joining us and for your presentation, and we'll see you soon. Thanks, Kristian.
Thank you very much. You're welcome. Goodbye.